Hello, this is Math Kimchi, and in this video I'll be showing you guys my code for a Connect 4 bot that uses Negamax, which is a variation of Minimax. And before I get into this video, I'm just going to say that I have previously made a video on Connect 4 bots. It was about the Monte Carlo algorithm, I believe, and I also have made a video on Minimax, which will both be in the description below. But anyways, the reason why I'm kind of redoing my two videos is because I am not sure if I completely went over the Minimax for Connect 4, because I know I did Minimax for tic-tac-toe, but I'm not sure for Connect 4, and I do have my old Connect 4 code, but even that old code was made better, and I've started from scratch again, and I think this is much better than my old code. And yeah, let me just show you guys the basic structure of my code. So this is the main loop that runs. So basically this function is called, so if we break this down, we have a game, and in the game it takes in a player 0 creator, which is going to be a function that takes in a board and returns a player of some sort. And yes, it also takes in the width, height, and a boolean, and the width and height are going to be 7 and 6. It's hard to see with this, but if you look here, it's clearly 7 by 6, and you should display just makes it so that it prints out the board, and that's pretty important because we want to see the game happen. And so we create a new game, and we call it dot start game method, and all that does is it starts the game. So yeah, start game is just a function, and it keeps on printing the board and asking each player to make a move until the game ends. And yeah, it's just a simple while loop, and it checks if the board is done. And first of all, I think I should explain why I'm using a function that creates players rather than a function that rather than just taking in a player. And the initial explanation was that I want the player to be made with board, but then you could say, why not just create a player and then have every player have like a dot set board function. And to be honest, I'm not really sure why, but I think this is just better. I just like it better, but the other way might be more clean. And anyways, yeah, there's a class called game, and inside game is all of the general logic, and I wanted this to be as broad as possible. So except for the print board, this is going to be pretty much the same logic no matter what game you have, as long as it's like a standard 2-player turn-based game. And so yeah, this is like the real basics. And inside of game, there's a class called board, and the board just has it's basically just two bit sets, and a bit set is basically an array of booleans. So it's gonna have values like, it's gonna be like array of true and false, or zeros and ones, if you prefer to think of it that way. And yeah, you can also just think of it as like a integer that's represented in binary. And there's two bit sets. The first one, pause, is for position, and what it is the position is where the current player's pieces are, and mask is where the opponent's pieces, or where everyone's pieces are. So, for example, if we had something like this, the current player is going to be, I guess it's yellow because yellow just went. And so yellow's gonna, if we had the position and we wanted to look at that, all of these empty ones are gonna be zero or false. And these two red ones are also going to be false, but these two are gonna be true. And the mask is gonna be false for all of this, but for these four, it's gonna be true. And if we do this, the only thing that changes with the mask is that there's one additional true. And with the position, these three are going to be true, and the two previous positions are going to turn into false. And so to basically do a move, all you have to do is turn the position, turn the mask to true, and you just take the exclusive OR, so XOR of the mask and the position to get the new position. And yeah, XOR is basically when, I guess it's the same thing as is not equal to sign. So there's OR, which if it's like a single one of them is true, but XOR is if exactly a single one of them is true. So if it's true and true, then it's gonna return false. And that's basically how you do a move. And yeah, if you look at all of these board functions, you're gonna see that I use something called board functions as opposed to just having all the logic inside of the board. And that's because I want some of these to be private, and so I want it to be like easier to, I guess, yeah, access these functions from outside. And a good thing about that is, I guess, you don't have to worry about accidentally messing up the original board. And so it's currently impossible for any player to mess with the game, which I think is nice. And anyways, the board functions has all of the connect for logic in it, and so yeah, it just is done. So it checks for either a win or a tie, and this checks for a win. You just look in all, I guess it's not always 4. You could set your custom connect size. So if you want it to be 5 or whatever, that's gonna be a pretty hard game, but sure. And it's full. It just checks to see if there's a tie, but obviously it could be full. But if there's also a win, then it's gonna be a win rather than tie. And is legal, it just checks the top of the column as winning move. It looks at every legal move and checks if it's a winning move. And to see if it's a winning move, it creates a duplicate and then makes the move and checks if it wins. And then to duplicate the moved board, when do I use this? Oh, I guess I create a new board, and apparently I use this exactly once. But yeah, there's also make move, and this edits the mask and the position, and has piece. It looks at a specific coordinate to see if if the mask is true or not, and this does the same thing but for exclusively the current player's position, and this takes the XOR of has piece and current player. So it's, yeah, this is the exclusive or syntax or operation. And get legal moves, yeah, it just looks at all of the top ones and sees if it's a legal move. And yeah, I think that's pretty simple. And let's see. Yeah, I mentioned that a game takes in 2 player creators, and the player, let's see, is just a single interface with something called get move. Can I make this a functional interface? I guess I can. So, I don't know. I'll do it then. But anyways, yeah. I have 2 main players. The first type of player is the human player, and just asks the player in the console for the move. So it's gonna go like, oh shoot, I was making it play computer versus computer. But yeah, simply if we do something like this, this is gonna be the human player that asks to type a column, but also it's assisted, meaning that the human player can see what the computer thinks is the best move, but the human has to, I guess, be the one to approve it or just go with their own thing. And there's also the score-based player, and this to create a score-based player, you need a scorer and also I guess the board. But the score is the most important thing, and all it does is it it looks at all of the legal moves and it asks for the optimum score, and from that score it's able to find the best score. And if there's multiple best scores, all it does right now is it does the very first one, but it would probably be better to choose any of them at random. The reason why I'm doing this right now is just because I want it to be more consistent for testing purposes. And yeah, to look at a score, I guess this is also a functional interface. Oh, and this time I did say it was a functional interface. Yeah, this doesn't it doesn't necessarily have to check for wins or losses, but a scorer takes in a board and it returns the score relative to the current player. And yeah. And in my old code, I'm pretty sure I always scored everything based off of player one, but that's just doesn't make sense because then you also have to. Well, it does make sense, but it's a little more complicated in a unnecessary way because it means you have to keep track of who's the first player and who's not, and especially in the way with the position and the mask, there's not really a useful difference between the first and second player. And so yeah, I just thought it would be better for all of the scorers to score relative to the current player. And yeah, this does the negative of the score, and that's because it wants to, yeah, because if the score based player was the first player and it did all of these, it made a move in a temporary board or a copy of one, and then it scores it using score, is going to score it based off of player 2. And since Connect 4 is a zero-sum game, meaning if I do well, then my opponent's doing bad, and vice versa. That means my score is essentially just the negative of my opponent's score. And so we can say that if this was player 1, the score-based player was player 1, then this would be based off of player 2. And to make this based off of player 1, we just do the negative of it. And yeah, we check to see if it's the best score and add it to the list of best moves. And there's 3 types of scorers I have right now. It's the Monte Carlo scorer, and this one I made a video on. And what it does is it just keeps on playing random moves until the game ends. So in a way, it's similar to Minimax, but while Minimax looks at every possible game, Monte Carlo just looks at one random game or 10 random games or 100 random games, and using that win-loss to tie ratio, you calculate a score based off of that. And I'm basically just increasing the score every time there's a win, and decreasing it every time there's a loss. I don't know why this is negative and positive, but I don't know. It might be because I was doing it for the Minimax, but that doesn't matter right now because that's not really the focus. But you can see that it's a pretty simple loop, so it creates a copy of the position in the mask. Oh, and by the way, when you do board.getPause, it doesn't actually return the true bit set. It makes a clone of it, and that just makes it easier for everyone because you don't have to worry about accidentally changing it. And moves count, it's just a count of how many moves it has been, and it's going to be useful to see if it's the first or second player, but also to see the score. And generally, if there's a win, then you want the win to be as soon as possible. And if there's a loss, you want the loss to be as far as possible. Uh, and in a Minimax, it's not really going to matter if you're assuming that both players are perfect, but even in the real world, it's going to matter more because it means your opponent has a higher chance of messing up, even if they had the winning position. So it's just better for you. And yeah, right now when there's a tie, I don't do anything, and this is just doing a random move, and yeah, it's pretty simple. It's a pretty simple algorithm, and I think it's not that good, but it's really easy to implement, especially in other complex games like chess, or at least I assume so. Because you only need to get a list of legal moves, and you're not gonna have to worry about um, scoring the leaf nodes like with Minimax or Negamax. And that brings me to the next score, which is Negamax. And what Negamax is it's just a variation of Minimax, where, if you remember, Minimax was the root player is the maximizing player, and the other player, the opponent, is the minimizing player, and you kind of alternate between maximizing and minimizing, and all of the scores are based off of the maximizing player. And it makes sense why it's alternating between max and min, because the maximizing player is the one whose score is based off of, and you want to increase your own score as much as possible, right? But if we were doing it off of your opponent's score, you want to minimize your opponent's score, because in a zero sum game, that's maximizing your own score. But what Negamax does is, since your opponent's score is just your score but negative, why can't we just score everything based off of the current player? And uh, all we have to do is, before we do anything, we just make it negative to base it off of our own score. And so you can see we're finding the maximum after making the score negative. And this makes it so that we never have to worry about if it's the first player, the second player, the maximizing player, and the minimizing player. We can just always call the maximum of the negative. And you could also think of it as it's still alternating between maximizing and minimizing and maximizing, since the negative, so the max of AB is going to be the negative minimum of negative A and negative B. And that's just another way of thinking about it. But yeah, it also makes it also makes sense to just say that we're always basing the score off of the current player relative to the board. And yeah, let me go through the code for the Negamax. And so yeah, nothing is too weird here. I guess the transposition table is just a hash map that stores all of the positions or boards that we've seen so far, and that's the key, and the value is going to be the score that we gave it already. And since it's the exact same board, we're going to know that the score is going to be the exact same. So for example, if we have there's multiple ways to reach a single board. So if we have something like this, it's a very simple example. But the score of this is going to be the same thing as the score of this. So why calculate it again? Why can't we just go, oh, I remember this, and look at what we have scored this previously and just not have to calculate it again. And that's what the transposition does. And there's going to be better ways to store it, like, oh, this is going to actually have the same score as this, because it's just the same thing flipped over. But right now it's just the very basic, where it looks at the exact same position and no reflections or anything like that. And get score is, this is what the score based player is gonna call. And there is a get score for this, but can I make this private? Yeah. This is like, I guess, the node, and this is like the root, or the very parent get score caller. And you can see that every time you want to get the score, you need to tell it the current mask and position, so we know what we're scoring, and the depth, so that we don't just keep on going until there's a game end, because that's going to be like so much to look at, and it's going to take, I don't know, maybe years, probably not years, but yeah, a long time. And then there's also alpha and beta, which is for alpha beta pruning. And what alpha beta pruning does is, when alpha is greater than or equal to beta, it's a guarantee that this position's never actually going to be reached in real life, I guess. If both players are playing optimally, that means that this current board will never be reached, because it's just a bad move for either alpha or beta. And yeah, it's like kind of weird, but it also kind of makes sense in a way. And this allows for you to score less nodes while also maintaining the same accuracy. And that's really nice, because usually when you don't score certain nodes, you're going to assume, it's like generally assumed that the accuracy is also going to be a little less. But no, the accuracy, if you do this correct, then it's going to always be the same. So next, we have the transposition table to check if we've already been here. And then we check if this has been 1 before. And if it has been 1, we return negative infinity instead of positive infinity. And that's because this is before, we're checking this before we've actually made our own move. And that means that the opponent was the one who just went relative to the current get score function. And so we want to say that our opponent is going to win. So that's negative infinity for us. And I also did have something for the winning move, but yeah, that doesn't really matter right now. And we can also check if there's a tie. So if board functions is yeah, if every position is filled or every mask is filled, then that means it's gonna be a tie. And in a tie, no one wins, no one loses, so that's just a 0. And finally, we check if the depth is greater than or equal to max depth. So if that's the case, it means we're not gonna know the answer for sure, but at least we're going to have an answer, as opposed to waiting like 2 hours just to score a tiny portion of the game. And yeah, this is going to be based off of the opponent as well, because we haven't made the move yet, and so we call the scorers the heuristic scorer, and ask what it thinks the score should be. And this is going to be a worse approximation than the Negamax, because obviously, since it's the heuristic score, and a heuristic score is something that's less accurate, but it's a lot faster, meaning that it's going to be useful in cases like this, when we want to score leaf nodes, when there's going to be thousands of leaf nodes. And for that, I think right now we're using a naive scorer, but I can explain that later. And anyways, next we have a array of all the legal moves, and this is pretty simple. We just ask the board function for all of the legal moves, and we calculate the heuristic score for each legal move. And the reason why we do this is so that we could sort the legal moves from best to worst. And from that, the reason why this is useful is because in normal Minimax, it's not going to matter, because we're going to check all of the branches, right? But in alpha beta pruning, it's better, if we can, to look at the better game trees, or the more likely ones first, because then it's gonna help us narrow down and go, oh wait, if the branch we already visited is better than what we think our current branch is, then we don't have to look at this anymore. So that's kind of what alpha beta does. And if instead we go from the worst to best, or an approximation of worst to best, then the alpha beta pruning's gonna do less work, because it's gonna be, oh, the branches we've looked at earlier are less likely than the current branch we're looking at, and so it's gonna be less likely that the conditions for alpha beta pruning is gonna be met. But anyways, we have the value, or the score, and it starts out as negative infinity. And a quick note is to not use integer.maxint, and that's because let's see, this will work. If we do integer.maxint, I guess that. Right. If we just have something Here to pause it. All right. If you have integer dot max int, it's gonna be what? Oh, max value. Yeah, it's gonna be a pretty big number, and min value is also gonna be a very small number. But we can see that the max value is actually less than the min value in terms of absolute sizes. And so what this means is that if we take the negative of the min value, we still get the min value, because what it's gonna try to do is it's gonna try to do this, but then yeah, it's gonna be out of range because it's greater than the max in value. And if we do integer dot max value, and if we do +1, essentially it's gonna be the same thing as this number, but then that resets. It's like so big it resets, and that is true with the min value as well. If we do min value -1, it's gonna go all the way to the max value. And yeah, I just thought that was something important because that's something I didn't realize. And I was working with integers because integers are just faster and nicer to work with. But yeah, if you're gonna try your own Minimax in Java, then you should probably do negative infinity using doubles. But anyways, yeah, this checks if the legal moves are empty, but this should never be run, or this should never like be possible. And I just have it just in case, and so far it hasn't triggered yet, which is a good sign. And yeah, so from here we're looking at all of the possible legal moves, and we're creating a copy of the mask in position so we can make the move without actually impacting the original. And we make the move and we calculate it using the Negamax again, and we increase the depth, and we search around the beta and alpha and negate it. And yeah, this, to be honest, I just copied the pseudocode for alpha beta pruning on Wikipedia. So yeah, but anyways, we look at the max value, and alpha, I guess, is also the max value between alpha and value. And if this condition is met, then it means that this game is never going to be possible, and there's no use in looking at it anymore, because even with the better scoring of this, it's not going to be used at all. And so we just break and return whatever we have so far, no matter how bad it is. And next, we just update the transposition table to show, so that we remember next time we get the same exact board, and then we return the value. And additionally, I reset the transposition table every time we score, and this is good because if we have if we started out from nothing and we look at this and we say this is like a score of I don't know, 5 or something. And the depth is, yeah, 5. And but then now we actually did get to this position. Then we're just gonna return that the depth is 5 anyways, if we don't reset the transposition table every move, because we want to reset it so that the outdated numbers with the old dates or with the old depths get updated. And this is yeah, this is just the best way of doing that, I thought. But yeah, essentially the hope is that I also do make like a opening book. So what while this is updating every possible move, uh the opening book's not gonna update a single time. It's just gonna be like a static thing, uh basically a constant. But yeah, that's something to think about for later. And all right, I have to let's look at the naive score. So if we compare the naive score and the win check, then you're gonna see that these are very similar to each other, and that's because while the win check looks at every possible connection and sees if it's like all connected with one player's pieces. What naive score does is it looks at every possible connection and it creates an array to go along with that connection. And so it's going to be the size of the connect size, which is going to be 4 in a standard game. And with that array of integers, where 1's going to be the current player, 0 is going to be no player at all, and -1 is going to be the opponent. We just take that, and basically what we do is we're going to return the sum and cube it, but also if there are both pieces in that line, then we just return 0. So if none of these have potential to be filled by either player, then we return 0. But if it's equal to 4, then we return infinity, positive or negative. And we should make this the connect length, but that's something for later, actually. Yeah, I can just do this. All right. All right. And yeah, so basically all naive score does is it breaks apart the entire grid into a bunch of uh, one-dimensional arrays of size 4 usually. So I don't know, it's kind of similar to how neural networks work in a way with like vision processing with kernel. Uh, but yeah, it basically looks at every possible connection, and if there is a possible connection that's open, then it just scores it uh, by calculating the sum and cubing it. And yeah, the final naive score is going to be the sum of all of the linear scores. And I could probably make a linear score another functional interface, but I don't know, I think that's kind of unnecessary. And yeah, I guess I can try playing a simple game with the Negamax. And yeah, I've been checking it, and on the most part, um, if it's the first player, then it's very smart. It's even with max depth of 6, I think I was able to do all of the best moves, at least against another depth 6 robot. So AI, I mean, and yeah, let's kind of see what happens if we just follow the advice. So actually, yeah, we could do what this computer wants us to do and compare it. And first of all, if you didn't know, Connect 4 has been solved by people like this guy. I think his name is Pascal Pons. And yeah, it's been shown that if two players play optimally, then it's always guaranteed that the first player is able to win, no matter what the second player does. So, yeah, Connect 4 is not like a fair game. And let's see. It's saying that the best move is this one or this one, so it's gonna be 2 or 5. And this wants us to do 2, so far it's pretty perfect. And then yeah, the other robot did 2, and now it's saying to do 2 again, which I agree with. And this also agrees. And the other Negamax did 1, which is actually the worst move it could have done. But then again, all of these are losing moves, and it's just a matter of how long you can draw out your own death. And technically, 5 is going to be the best move, but it doesn't really matter because all of these still keep a winning hand. And yeah, it just did a 2, and now it's saying that we should do a 5, which still maintains the winning move. And whoa, all of the moves except for 6 apparently was like a death in 6 moves. And yeah, this also agrees with that. Yeah. Now this wants us to do 5 again, which is, it's not the best move technically, but it still wins, so I mean, I'd take it. And it did a 3, and now we should do 5. Alright. Yeah, it's pretty obvious I should do this. But next, it's it wants to do either 2 or 5, and these two are both winning moves, so I'm just gonna do the leftmost one. And yeah, the other bot did this, and now we want it to do 5 as well. Alright, and the other bot did 0, which was the best move. And now it's saying we should do 0 again, and yes, this was the winning move again. And let's see, it just did another move here, which is the other good move. And yeah, we can either do 0 or 1. I'm just gonna keep on doing the leftmost one if possible. And wait, what? Yeah. And now it's saying the best move is 1, so we can do that. Wait, what? Oh. Oh wait, yeah. So I did that, and it did that. Alright, so yeah, that was the other good move. And now it's saying if we don't do 4, everything else is a losing move. And the bot agrees as well. The other ones we lose in 7 moves. I think that's what it means. Alright, and yeah, so we do 4, and it's saying that the bot did another 4, which was the best move. And now, yeah, if we don't do it, we're gonna lose to the diagonal, and it saw that as well. And yeah, the other bot just did another 4, I think. And yeah, now it's saying all of our scores are infinity, and I guess an unintentional side effect of turning it from a integer dot max value to a double dot positive infinity is that now it looks better on text. But anyways, it's saying that the best move is 4, and it agrees, I think. And yeah, now the bot's just gonna keep on doing 0, and even if that's gonna make it lose sooner, it has no concept of that, since it's all dealt with in infinities. So a loss immediately is the same thing as a loss in 10 moves to the bot right now. I guess it wouldn't be 10. A loss in 1 move is the same as a loss in 6 moves according to this bot, because right now they're all being treated equally worse. And so now it's just gonna give up and keep on doing the left most available move, which is kind of sad, but Yeah, just did one again because that's the leftmost move. I guess even if I do 6, the other bot's gonna do 4, I assume. Yeah, because both of them were bad. And now we don't really have to check in with the computer. Oops. Oh wow. Yeah. I was gonna say we don't have to check in with the solver anymore because it's just gonna be one row. But I guess that was the win. And yeah, even though we could have won sooner technically, I think that this is still uh, just as good since we were able to win anyways. And I think that's, yeah, for a Connect 4 bot with a depth of only 6, I think that's pretty good, at least for the first player. And yeah, thanks for watching this video. If you want to see more, then the link will be in the description. And yeah, thanks for watching. Bye.